Hi, so this is going to be a small tutorial over uh, runtime configurable transform length FFT and how we can implement it on the PYNQ workflow, and we will look into how we can design simple hierarchical drivers which can make it easier to use these type of implementations. So I have starting with the block design for the FFT implementation, and I have already created a project with PYNQ Z2 board as my project device. I have also created a block design under the name of Reconf_FFT. So I will quickly add my blocks in this block design. First I will add the processing system, run the block automation. Once that is done, I will enable the HP ports for my DMAs to send and receive data from. I will add my DMAs for the FFT block itself. So I would be adding two DMAs, one for transferring the data and one for transferring the configuration. So first of all, let's start with the data DMA. I would be sending 8K values, 8K complex values for my FFT IPs. So I want my buffer length register to be at the maximum value itself. I will increase the memory width size and the stream width size to 64 because I would be sending 64-bit data, and I will increase the burst size to maximum for both read and write channels. This is set to auto, so it will automatically detect what the write channel size is and automatically configure it accordingly. So once this is done, this is how my data DMA would look like. It would have a disabled scatter gather engine, and I have increased the buffer length register to maximum and increased the memory map width size and the burst size for both read and write channels. So once this is done, I can rename it to something like data_DMA, and now I will add another DMA for the configuration part of my FFT. So here comes another DMA. Again, I will disable the scatter gather engine, and for the configuration DMA, I would be sending only a single integer at a time. So I do not want it to be I do not require a very large buffer length register. I can just keep it to be 8 bits for now, which is the minimum value. I would not require any writes to the memory itself, so I can disable the write channels as well and keep the read channels as it is. So for my configuration DMA, the scatter gather engine is disabled, the buffer length register size is reduced to the minimum possible value, and there are no write channels required in our config DMA. So once that is done, I can keep it like this and rename it to config_DMA. So I have added both of the DMAs now. The data DMA is data DMA and the config DMA, and I can start by running connection automation over this. So I will just start by connecting these DMAs to the processing system itself, and let's regenerate the layout once. And this is how your end system should look like. The processing system now connected to the config DMA and the data DMA through the smart connect via the HP ports, and these both DMAs are configured via the GP port through the IIIT ports that are given in the config and the data DMA. So these are the major connections that are required. Now I will go ahead and add my FFT IP, which we will first configure and see how we can what changes are required in that. So here is the FFT IP itself. I can open the FFT IP and change some of the parameters inside it. Okay. So first of all, I will change my transform length to 8192, as it will give me uh, some values that I can change from. So for example, I can change from 8192 down to 1024 or to 4096. So this is the maximum transform length it can the FFT IP can go to, and I can enable the runtime configurable transform length, because I want this change in transform length and change in transform length to be available for me in the case of fast Fourier transform IP. So now in the implementation part, we can go ahead and change my data format to floating point, because I would be sending floating point values from my PS rather than fixed point values. And once that is done, I will enable the reset signals and change the output ordering from this digit reverse order to natural order. Okay, so now you can see I have changed it from floating point, I have added the reset signal, I have changed the output ordering to natural order. Sometime it might happen that the detailed implementation tab might give you problems. So one thing that you can do to kind of resolve it is to change some of the values from one to another and come back to the same value. So this kind of refreshes it and it comes to a consistent set. So as you can see, I have changed the values and it has come to a consistent set. There are no red tabs as such. And now the major changes that we have done is increase the transform length to 8192, enable the runtime configurable transform length, and change the data format to floating point rather than fixed point, add a reset signal, and change the output ordering to natural order from digit reverse order. Other than that, there are no changes and we can leave the FFT IP as it is. So once this is done, now the only thing we need to do is connect this IP to the config and the data DMA. So once let's zoom in this area and see how we can connect them. So here, so first of all, let's connect the configuration part. Here is the configuration part, and this will go to the master port of this configuration DMA goes to the slave port, which is the configuration port of the FFT IP. So this is the one connection. The master port of the data DMA goes to the slave port of the data DMA. This is also connected. The slave port of the data DMA goes to the master port of the FFT IP, which is the master data port. Once these are connected, you will be get a run connection automation pop-up, which will connect your clocks and reset signals to the appropriate areas. So the clock and the resets are now also connected. Before proceeding any further, let's now make a hierarchy to make our design a little bit more easier to view. So I will just right click on one of the objects from config DMA, data DMA, or the FFT IP. I will just create a hierarchy and I will name it FFT underscore block. Once this is done, I will press OK. So now let's regenerate the layout. Now the one of the IPs is in the FFT block. I will just drag the other two IPs inside the FFT block itself, just to redesign the layout. And now you can see that my FFT IP, both my DMAs are inside this FFT block itself, and I can double click and I can see how they look like. So here is my data DMA, here is my config DMA, and here is my FFT IP, which are inside the FFT block itself. So I can just regenerate the layout to make it a little bit more easier to visualize. Once this is done, I can start by validating my design. And I should get an warning that says that the tnum bytes does not match between this specific port, which is my FFT IP configuration port, and the port from the FFT config DMA M axis MM2S. So the config DMA master port and the slave port of the FFT slave configuration port of the FFT IP does not have the same number of bytes between them. So let's see what exactly that warning is. So if I open my MM2S port, you can see I have the data of size 32 bits. So 32 bits of values are sent from this port, but the configuration port here only take 24 bits of value. So the data that the configuration receives is only the 24 bits value. So what does this mean is the upper 8 bytes are not kind of sent from the configuration DMA to the configuration DMA to this specific configuration port, and only the lower 24 bits are sent to this configuration port, and which is kind of that is kind of the error we are not error but a warning that we are getting in our case. So this is not a big deal for us because we have this in mind that the configuration data is only 24 bits. So any 32 bit value that I write to my configuration DMA would be sent, only the last 24 bits would be kind of received by this FFT IP, and that is one of the things that I should keep in mind. So once this is done, what we can do is we can start by creating a HDL wrapper over this. And we can start by generating the bitstream itself. So now since bitstream generation will take time, we will continue once the whole bitstream is generated. We are done with the bitstream generation now, so we will export the hardware, and after that we will go to the PYNQ workflow and see how we will write the code for this reconfigurable FFT. So I will just choose a location which will have my bitstream and the other files that I will require. So once this is done, so here I have the HDF file which will contain my bitstream file and the hardware handoff file, and this is the recon_FFT hardware handoff file, and this is my bitstream file that I will require for the PYNQ work. I will just rename this recon.wrapper rename this to recon.fft. And now we will copy this to the PYNQ board, and we will see how the code looks like. So I have already copied my bitstream and the hardware handoff file inside my PYNQ board, and let's start with the basic implementation of the code itself. So first of all, I will import the overlay. I will generate an overlay object using this class and the bitstream file that I have generated. After that, let's check how the overlay looks like. So there is the hierarchy of the FFT block that we have made in our block design, and which is connected to our default hierarchy object for now. And then there inside the FFT block there are two IP blocks that we can see, the config DMA and the data DMA, which are directly connected to your processing system or the PS. And the FFT IP itself, which is a streaming IP, is not visible because that has no direct connection to your processing system. So now we will make simple aliases for our data and config DMA, and after that I will just get the send and receive channel for my data part, and for my config part I only need the send channel because I will be only sending the configuration to the FFT IP itself. We need to make sure we do not make a receive channel for the config DMA because that does not exist in our block design that we have created. So once this is done, let's see what actual configurations that we need to send to the FFT IP itself, because that would be responsible for configuring your whole FFT blocks, how it should behave, and what size of the FFT should be when during the whole sending and receiving process. So we have already seen the data part looks like this. There is a 24-bit data that is present, and this 24-bit data can be divided into 3 individual bytes. The first byte is responsible for the individual channel forward and inverse FFT. So if I want to configure the individual channel as a forward or inverse FFT, I would be changing some values in the first byte of this configuration that I want to send. After that, there is cyclic prefix length, and since we are not using it for our case, we will be leaving it to be all zeros for now. After that, the third byte is responsible for the size of FFT over all channels. The thing that we need to remember is all the channels will have the same size for a given FFT block itself. So let's take an example. So in this case that I have shown here, we have a padding of 5 bits. This tells us that there are only 3 channels that are kind of accessible in the case of our in this specific case. So basically the first bit is 1, which says channel number 3 would be a forward FFT or a normal FFT, and the remaining 2 channels, which is channel 2 and channel 1, would be a inverse FFT. After that, once this is done, we have padded this to a whole byte, so 5 additional zeros are added in front. After that, there is a single byte which is cyclic prefix length. I have currently left it to be all zeros because we do not need this. And after that, we need the size of the FFT. So since the size of the FFT is also a 8-bit long value, I cannot write the whole FFT size. For example, if my FFT size is 8192, I cannot write the binary value 8192 inside this specific 8-byte value, as it might overflow. So what we have done is, basically we take the value whatever FFT size is and we convert it to whatever 2 to the power it should be. So for example, if our FFT is 1024 size of 1024, we will convert it, we can write it as 2 to the power 10, and we will take this power, whatever it comes out to be, and set the value of this individual byte according to that. So for example, in case of 1024, it comes out to be 10. So I will convert 10 into binary value, and I will write the whole write the specific binary value here itself. So this way we do not require as many bytes to show that what is the size of the FFT itself, and we can have bigger FFTs written here as bigger FFTs like 16,000 or 32K written here without using multiple bytes of data itself. So once this is done, what I can do is I can kind of configure make this whole T data using 3 bytes, right? So let's see how it looks like into the code itself. So first of all, let's start with this convert to data function. There is this FFT direction which is kind of telling me what direction my FFT wants to go in for an individual channel. In my case, it can be a forward FFT or inverse FFT on individual channels, and the size of the FFT, which can be 1024, 16K, 8192, and something like that. So FFT direction is a binary string, so it's just a normal string which has either zeros or 1 as values, and the size is just a integer value which is which is some power of 2. So in the FFT direction, what I am doing is I am filling it to be a 8 string of size 8. So for example, if my FFT direction is 0 1 1, which means my channel number 3 is 0, channel number 2 is 1, and channel number 1 is again 1. What I am telling FFT using this zfill function is kind of prefix zeros in front of this whole 0 1 1 until this becomes a string of size 8. So by this I kind of pad it to a whole byte itself, and after that I need to, once I'm done with this forward byte, I need to figure out the second byte, which is all zeros. So I have just created using a string repetition, I have created the byte 2, which is cyclic prefix length. And now I need to figure out what power of 2 is required in this, what power of 2 is my size of the FFT, and fill that binary value here, right, in the last byte itself. So for that, what I am doing is I am using log base 2 to find out what power of 2 is required in this case. So this x is the power of 2 which I get, and I am converting it to the binary value of that specific power. This gives me again a string of random size, which would be less than 8. So what I am doing is I am using FFT size, and I am again using zfill to kind of prefix multiple zeros in front of it to pad it to a size of 8. Once this is done, I have my 24 bits, and I just need to concatenate them and create the T data itself. So there is your FFT direction, then there is your byte 2, which is all zeros, and then there is your FFT size string. So this all gives you a 24 bit a binary string of size 24, and after that I am just creating an integer out of it, because rather than I want a integer rather than having individual bytes of the string itself. So just creating a string out of integer out of it, giving it a base of 2. I am passing the T data, and the integer should be able to convert this to a integer, which kind of resembles this specific T data values with zeros preceding it, a single byte of zeros preceding it, because our integer is a 32-bit long value, right? So once this is done, now we can start with our software implementation and see how it differs with the hardware implementation. So currently, when there is no configuration passed to the FFT IP, it kind of defaults to the maximum size of the FFT that was configured, and all the channels are forward FFTs or normal FFTs. So for now we will start with the software implementation. I am taking the samples to be the max samples in our case, which was 8192. I am creating I have a function that creates 3 different sine waves of random frequencies and random amplitudes, and after that I am just plotting out the data using the pyplot functions, and this is how our 3 sine waves look like in time domain itself. Now I will just create the FFT, and we can see that the time taken by the software implementation is between 5 to 15 milliseconds, which is kind of expected because the size of FFT is kind of 8192 right now. So after that, let's try to plot the output of the FFT that we got, and here are the results of the 8192 size FFT that we had. So currently you can see the 3 individual sine waves that are plotted as the frequencies graph is present here. So you can see the size of the FFT with the help of the x-axis. It starts from -4000 to 4000, which kind of tells you that the size of the FFT is in the range of 8000 itself. Now let's start with the hardware implementation and see what happens. So currently I am using the allocate function to allocate my buffers for my DMA. I am using C single because my FFT IP uses 64-bit values, 64-bit complex values, which is 32-bit real and 32-bit imaginary, and I am copying my buffer, my data into my input buffer itself. So just plotting out how my input buffer looks like, which is very similar to very similar to the data we have plotted here. Now I will just time my send and receive. I will just send my input buffer and receive my output buffer and wait for both of them to complete. For this, you can see that timing jumps from 1 to 5 milliseconds, and which is like not considerably, but faster than the CPU implementation for the case of 8192 size FFT. So now we can see how the output buffer will look like and plot the output itself. So you can see there is a very similar graph present here as well for in the case of the hardware implementation as well. And now we can shift towards reconfiguring the FFT itself and seeing the output of the seeing the output on a smaller scale. So now I will change my sample size to 1024. I am changing my sample size to 1024. I am creating new data based on that samples that I have. So 1024 samples. Now I need to use the configuration DMA to send a configuration which tells my FFT block to do a 1024 forward FFT. So to do that, I am allocating a single a buffer of size 1, which will send a uint of size 32. Yeah, we remember that we are sending a 32-bit value, but only the lower 24 bits are used by my FFT. So this should not cause any problems. And in this case, I am using the 0th value of that configuration buffer that I created, and I am sending the value of convert to data. I am telling it that I want to do a forward FFT on my channel 1, which is my last channel, and I want to do a forward FFT of size samples, which is 1024. So once I have set it, I need to send this whole buffer to my configurational DMA. I will do it using configuration DMA transfer configurational buffer. This buffer is sent, and I will wait until it is sent. After that, the whole process repeats for sending and receiving the data from the FFT. I will allocate another buffer of size 1024 in this case, because the sample has changed, and output buffer of size 1024, and I will copy the data to my input buffer itself. So once this is done, I will again send my input buffer, I will receive something in my output buffer, and I will wait for both of them to do all of their jobs. Once this is done, I will basically plot this whole values, and you can see I have a similar, but I have a value which is from 0 to 1000 value. So it is around 1024 values, and the FFT is between 0 to 1024. We can do a software plot pretty quickly as well, and you can see there is a very similar plot generated for the software and the hardware part of the implementation, which is also coming out from 0 to 1024 values. So this is how you can do a simple reconfiguration of the FFT using these two DMA approach. One of the things is when we are doing this whole FFT implementation, we really we were doing a lot of code copying pasting. For example, in the case of configuration, in the case of sending and receiving the data, all these things are done on a very regular basis, and we need to we have the problem of code redundancy. So as you can see in the case here, for the 20 or 8192 case, we were sending the data and receiving the data into input and output buffers, and then plotting it and all that stuff. Similar thing was done for the 1024 size FFT. We were sending and receiving the data. Before that, we were just doing some configuration. So this all adds to some code redundancy. To prevent this, what we can do is we can try to create a simple driver which will connect to my FFT IP itself, or the FFT block itself, or the FFT hierarchy itself. let's have a look how exactly that happens. So basically now what I have done is, there is another implementation where I have created a FFT block driver which will be automatically connected to my FFT block whenever it sees that specific hierarchy. To do that, what I have done is I have imported a default hierarchy and I have made a class which is named under FFT block driver. FFT block driver is a class which is a child of the default hierarchy, and in this specific thing, in this specific class, we have two major functions that we have to kind of implement to make it connect to our overlay or our block designs or block hierarchies itself. So the first function should be the init function, which is responsible for initializing your class variables, initializing the super class variables and stuff. So basically the init function is taking two inputs. There is the self which is present, and there is the description variable. So this description is the description of the whole the description we get from the hardware handoff files itself. So what I have done is, first of all, I have called the super class init function, and inside that I have just passed the description that was passed from the hardware handoff file. Any of the variables that I might require in the functions below, which might have some state, I have defined in the initialization block itself. So I have used two variables. One is the configuration variable. So anytime I want to use that, I will use self.configuration should be 0 and self.FFT size, which is 0. Self is the object that you create from this FFT block driver itself. So self is telling that it has a configuration value which is 0, and self has a object or a variable that has a configuration. Self has a variable and named configuration which has a value of 0, and self has a variable which is FFT size, which is also set to 0 initially. After that, the another important function that we require, or a method that we required, is the this check hierarchy, which is a static method. So we have added a @static in front of it, and we check the hierarchy to get the idea of what is present inside the hierarchy, and if all the things that inside the hierarchy match, we kind of bind to that specific hierarchy itself. What does that mean is, basically I have a simple check that returns either true or false. If this function returns false, I will not connect to that specific hierarchy, and if it returns true, it will bind to that specific hierarchy. So in the case, I am checking that in the description, if there is a IP which is called data DMA, and if there is an IP which is called config DMA, if both of them are present, then this will return true, which means this whole function or this whole class will bind to that specific hierarchy itself. Once the binding part is done, we can use any of the functions that are defined under this class to do our work. So for example, I have defined three functions additionally. One is a internal function which is convert to data, which is doing the whole same thing that we have defined to generate the T data itself. Then there is a configuration function which is responsible for configuring the FFT block accordingly. So whatever direction and whatever size you select, it will use the convert to data function to generate a configuration. Then it will basically send that configuration to the FFT block using the configuration DMA, and it will configure your DMA using this single configure function itself. And then when we are ready, after doing the configuration, when we are ready to send and receive data, what I have done is I have created a simple stream FFT function which will take one input buffer and give you a output buffer back to you. So in this case, you can see this is doing nothing, just allocating output buffer, sending the input buffer to the FFT IP, and receiving values into the output buffer itself, waiting for both of them to get into the whole DMA process. and returning you the output buffer that was generated when through this DMA send and receive. So this is how my whole FFT block driver looks like. The main things that we have to implement are the init function and the static method, and all the things you define in this specific class can be used to make it a little bit easier to use your whole block design that you have generated. So let's see what happens when we now use this specific class. So I have ran this block. You can keep this class as a py file and import it normally as a driver, but I have written it here itself. So after that, I'm doing just the normal stuff. I am importing the overlay. I am creating an object using this recon.fft, and let's see how my overlay now looks like. So now you can see my overlay has changed from a default hierarchy function to FFT underscore block driver, because I have both the data and the config DMA inside this FFT block hierarchy, right? So now it is kind of attached to this specific class that I have generated, and now I can use any of the function defined inside the class to make it easier to work with. So now I will just, rather than going to the config and the data DMA, I will create a alias for my FFT block itself, and now I can generate a simple very simple code to do my whole calculation. So now I'm just doing a software implementation quickly for 1024 size FFT. So I have created a simple, again, a 3 sine wave of random wavelengths and random frequencies, random amplitudes and frequencies, and here is the software implementation for that. And after the software implementation, let's go to the hardware implementation pretty quickly. I allocate a input buffer, I copy my data into my input buffer, I configure my FFT. So rather than doing the whole FFT configure thing, what I have done, sending the data to the DMA and waiting for it, I am using the FFT configure function that was given. So the block has now a function called FFT.configure. I am sending it the required values, which is the samples and the direction of the FFT itself, and this kind of configures my FFT. And to do the hardware FFT, I do not need to now work with any of the data FFT or the data DMAs. I can do simply stream FFT function and pass it my input buffer itself. So once that is done, I will get my output, and now I can plot both the software and the hardware. So you can see the software implementation and the hardware implementation. So the software implementation and the hardware implementation pretty much coincide with each other. They both are of the size of 0 to 1000, which is 1024 size FFT. And let's see what's the difference between both of them. So the absolute difference between both of them comes out to be in the order of -2, which is present due to the computation differences between the FFT and software, which is done in 64 bits complex and 64 bits imaginary, basically a complex 128, but in our case it is done in single precision for real and complex, so 64 bit complex number. So this difference is kind of expected. So once this is done, we can now this kind of concludes the whole DMA, the reconfigurable FFT, and how you can kind of make it a little bit easier to use or easier to replicate when we design this kind of default hierarchy or hierarchy based block drivers for the PYNQ workflow. You can see that we do not require any multiple lines of code to do the same transfers and receives from the DMAs itself. We can just have a singular line of code for individual blocks, which makes it easier to easier to understand and more concise to use.